Students, welcome to Mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 11 to 15 of the August 2016 Geometry Common Core New York Regents exam. Now, if you have any questions in the course of this presentation, just feel free to post your questions in the comments section below, and we'll be more than glad to support you. All right, let's take a look at question 11. It reads, segment CD is the perpendicular bisector of segment AB at E. Which pair of segments does not have to be congruent? So in this case here, what we're going to do is give ourselves a visual so we can label it completely and determine which sides are congruent. So let's start with segment AB. Okay, so let's say this is segment AB, and then we have another segment CD that's a perpendicular bisector of segment AB. Okay, so let's draw something like this. All right, let's label it completely. The point of intersection is E, so this is CD. Now, since it's a perpendicular bisector, this will be a 90-degree angle, and AE will be congruent to EB. Okay, so AE congruent to EB or BE, so we see that statement number 3 is correct. Okay, that's always the case. We want to look for the statement that does not have to be congruent. Now, how about AD and BD? What can we say about those sides? So let's go ahead and draw those sides. So AD and BD, this is for option 1. Now, what do we know about these two triangles here? Let me call it triangle A, triangle 1, and triangle 2. What can we say about these two triangles? Well, they both share this 90-degree angle because of the perpendicular bisector. So we have angle, and then we have these two sides are congruent because of the bisection by the segment CD. And then ED is congruent to ED by the reflexive property. So we can easily conclude that triangle AED is congruent to triangle BED. So since congruent parts of congruent triangles are congruent, it automatically follows that AD is congruent to BD. So guess what? Statement number 1 is correct. Okay? So let's put that right here. So this implies that AD is congruent to BD. Okay, now the next option, AC is congruent to BC. Is that always the case or no? It's the same situation as option 1, but let me just show you what I'm talking about. Let's make this one red. So AC and segment AC and segment BC, are they congruent? Well, what do we have here? Let's call this triangle 3 and 4. Okay, triangle 3 and 4. What do we have going on here? We have these two angles are congruent. That's A because they're both 90 degrees. This side and this side are congruent. That's S. And then this side by the reflexive property, they're congruent. So you have another SAS situation. Okay. So using that congruency postulate, we can automatically conclude that triangle AEC is congruent to triangle BEC. Okay, so what does that tell us? It tells us that segment AC is congruent to segment BC. Okay, so this is true. So by method of elimination, we can automatically conclude that option E is the answer. It does not always have to be congruent. So D, E, and CE, just take a look at it. Okay, are they congruent? Think about a kite, right? So if you look at these two segments, they are clearly not congruent. So it could be true if we had a rhombus, but it's not only a rhombus that meets this criteria where we have the perpendicular bisection of diagonals. If you have a kite scenario, then the segments of the longer diagonal is not bisected by the other one. Okay, so we can clearly see that the answer is option number 4. It does not always have to be true. All right, let's take a look at question number 12. It reads, in triangle CHR, O is on HR and D is on CR. Okay, as illustrated in this figure, so that angle H is congruent to angle RDO. Okay, so angle H, this angle right here, is congruent to angle RDO, this angle right here. If RD is 4, RO is 6, and OH is 4, what is the length of CD? So we're looking for this length right here, length CD. Okay, so first of all, with this given information, we have a big triangle and a small triangle. What is the first thing that should come to mind? Could it possibly be that these two triangles are similar? Well, if that's what you're thinking, then you are correct. So how can we show that these two triangles are similar? So I just have a diagram right here. What I'm going to do is I'm going to orient the big triangle and the small triangle in the same configuration so that we can easily set up our ratios in such a way that corresponding sides are in proportion. Okay, so this is H, C, R. Okay, and we know that this angle right here is congruent to this angle. Okay, so let me take one of the small triangle out. Okay, pull that out, and I'm going to notice that this angle right here, I'm going to rotate it around so that it's in the same configuration as the other one. So let me put it back. So if I so this angle right here, let me mark it so you can keep track of the transformations happening. This angle right here, if I rotate this figure so that this angle overlaps with that one, angle R is going to be oriented with angle C, which doesn't work. Okay, so what I'm going to have to do first is I actually have to flip it and then rotate it. Okay, so I'll take this triangle, let me flip it real quick, flip it up, down, okay, and then I'm going to rotate it so that they are in the same configuration. Okay, so place it like that. Alright, so what am I trying to show you here? This angle RDO is right here. Okay, so this is D, and we have R has been rotated. This is still R right here, and then this is O. Okay, so this angle right here is congruent to that angle. This angle right here is congruent to this angle. So let's go ahead and mark it. They are the same angles. So CD, okay, this is supposed to be R. Alright, so this angle right here is congruent to this angle right here. So if you have two triangles where a pair of corresponding angles are congruent, what's the conclusion? The conclusion is that the triangles are similar. Okay, so triangle CHR is similar to triangle ODR. Okay, by the AA similarity postulate. Now that we have similarity, we want to set up ratios. So the reason why I configured them in the same orientation is we want to make sure that corresponding size and proportion. Okay, so we're asked to find CD. Let's put in the measures that we know. We know that RD is 4, so that's 4 right here, and OH is 4. Actually, let's do RO first. So RO, this is my O right here. RO is 6. Okay, OH is 4. So RO is equivalent to this long side of the smaller triangle, so this is 6 also. OH is 4. Okay, and then we are asked to look for the side length CD. Side length CD. Okay? Alright, now, first things first, let's use the similarity postulate to find CR, and then we'll subtract DR, which is 4 from CR, and then we can figure out what that's going to tell us what CD is. Alright? So, we have this side DR corresponds to side HR. Okay, so DR over HR, I picked these two sides because I know their measures. Okay, is equal to, I know OR is 6 divided by CR. Okay, so in the numerators we have the small triangle measures, and in the denominators we have the big triangle measures. So let's go ahead and do some more labelings here. Let me just move this down a little bit. Now, how long is HR? For HR, we have to do some arithmetic. This side right here, HR, is 4 plus 6, okay, which is 10, using the segment addition postulate. And CR, we do not know. We need to find CR, okay? So let's do that. Let's find CR. Alright, so to find CR, we're going to go DR is 4 over HR is 10, equals 6, which is OR over CR, which we do not know what it is. Now, how do we solve this ratio? You cross multiply, right? When you cross multiply, you have 4 times CR is equal to 60. And then you proceed to solve this resulting algebraic equation by dividing both sides by 4. Okay? When you do that, you have CR is equal to 15. So, is our answer 15? The answer is no. You got to be really careful. Make sure you're answering the question. The question asks for CD. Okay? This is an intermediate answer. It is not the final answer. So to figure out what CD is, we simply know that CR plus DR gives us CD plus DR gives us CR. Okay, based on this configuration right here. So let's write that down. We know that segment CD plus segment DR gives us the entire length using the segment addition postulate. CD is what we're looking for. We already know we're given the fact that DR is 4, and we just found out that CR is 15 using using similarity ratios, using the similarity of the two triangles. So you just subtract 4 from both sides, and then we have CD equals 15 minus 4, which is 11. Okay, so our answer is option number 3. Let me put it in the figure so you can see what's going on. So this is 4. The entire thing is, so from here to here, that one is 15. Okay, so that's 15. From here to here is 15. So when you go 15 minus 4, that gives you this remaining portion right here, which is 11 units long. So we just basically use the segment addition postulate and the similarity ratios to figure out the length of side length CD. D. Okay, so that's that. All right, let's take a look at question number 13. It says the cross-section of a regular pyramid contains the altitude of the pyramid. The shape of this cross-section is a. So what is a regular pyramid? Let's address that question first, and then we'll go ahead and solve the problem. So a real quick reminder of the definition of a regular pyramid. A regular pyramid is a pyramid whose base is a what? What do you think? Look at the name regular pyramid. So regular pyramid is a pyramid whose base is a regular polygon. Okay? Like a triangle, a square, a regular pentagon, regular hexagon is a regular polygon with all lateral edges of equal length. Okay? Alright, so if you have a regular polygon, then what does the cross section look like if the cross section contains the altitude of that pyramid? Okay, so if you think about the outline of a pyramid, okay, and let's say this is a square pyramid. If you're looking at it from the side like this, and you intersect a plane through it, because the intersection of the plane and the pyramid will give you the cross section. You clearly see that from the side view, it doesn't matter what the number of sides the polygon at the base has, but the side view will always give you the cross section, which will always be what? It is always going to be a triangle. It doesn't matter the number of edges, the number of sides that a regular polygon has at the base. Okay, so let's do a real quick visualization here using this software known as GeoGebra to show you what I'm talking about. Okay, so we're gonna take a look at different regular pyramids. Let's start with this one. Now, what kind of regular pyramid is this? If you look at the base, it has 3 sides. That's an equilateral triangle. This is a triangular pyramid. Okay, it's a triangular pyramid. Now, let's create the cross section in such a way that it contains the altitude. Okay, so I'm just going to try my best here because it's not that easy to find certain points by hand. So I'm going to draw a plane that goes through the midpoint of that other side right there and this vertex, and then it also goes through that vertex that's pretty much close to the altitude. The altitude should stay somewhere here. So there goes your plane. Okay, now let's take a look at the cross section. What is the cross section? Cross section is a triangle. Okay, so you see that the cross section that contains the altitude is somewhere there, that contains the altitude of the triangle. See that? See the altitude right there? The cross section is a triangle. Okay? Alright, so let's do something else. How about, I just changed it, sorry. How about we add one side to the base? What if we have a square pyramid? Okay, as you can see here. Now this one's easy to figure out where the altitude is. It's going to be on the diagonal, right? So let's put a point on the top, and then put a point right here. And I'm going to draw the cross section in such a way that it intersects these 3 points. And I know for a certainty, 100% sure, that it's going to be the altitude. You see how it lines up? Okay, so bam, there goes the plane. Now the intersection of this triangle and the plane, basically the cross section is what? What shape is that? Bam. It is a triangle. Okay, let's do one more. Let's do a hexagon. I don't want to do pentagon because it's too hard to figure out the altitude. So let's do hexagon. All right. So for the hexagon, I'm going to draw the cross section. Do you see what the cross section is here of this hexagonal pyramid? Well, all we have to do is draw a plane that intersects it, but in this particular case, we're making sure that the plane contains the altitude, okay? So that's what I'm trying to do here. Bam. So there goes the plane. That's showing the intersection of the plane and the hexagonal pyramid. And you can see what the cross section is. What is it? The cross section is a triangle. Okay, so that clearly shows that if the cross section of a regular pyramid contains the altitude, then that altitude is going to the cross section is going to be the shape known as a triangle. Okay, so that clearly shows that our answer for problem number 13 is option number 3. Alright, let's take a look at question number 14. It reads, the diagonals of rhombus TEM18 intersect at point 21. If the equation of the line that contains diagonal TA is y equals negative x plus 3, what is the equation of a line that contains diagonal EM? So something I'd like you to recall is the relationship between the slope of two lines that are perpendicular to one another. Okay, you might wonder, what does perpendicularity have to do with this problem? We'll talk about that in a second, but let's talk about slopes of perpendicular lines. Okay, if two lines are perpendicular, okay, basically they intersect at 90 degrees, then the slope of one line is the negative reciprocal of the other. It's a negative reciprocal of the other. Okay, so you don't just negate or reciprocate, you do both. Okay, so it's a negative reciprocal of the other. Alright, so let me show you what I'm saying in symbolic form. So let's say you have two lines L1 and L2. So if L1 is perpendicular to L2, then that implies that the slope of L1 is going to be the negative reciprocal of the slope of L2. Okay? Alright, so let's take a look at what we are dealing with here. We have a rhombus. Okay, and what do we know about the rhombus? We know that let's go back, let me see what it says here. The diagonals intersect at a particular point. So let's make a diagonal here, and then we have another diagonal right here. They intersect at the point 2, 1. Okay, 2, 1. The vertices are T, E, A, M. Okay, and we're told that the equation of one of the diagonals, namely TA, so the line containing this segment TA is y equals negative x plus 3. And the question is, what is the equation of this other line containing the second diagonal? So this line right here is y equals what? That is the question. Okay? So first things first, you want to remember that the diagonals of a rhombus are perpendicular to each other. Okay? So that's critical here. Diagonals of a rhombus intersect at 90 degrees. So let's put that point down. Since the diagonals of a rhombus intersect at 90 degrees, rhombus are perpendicular, then what can we conclude? We can conclude that segment TA is perpendicular to segment ME. Alright, so the lines containing these two are going to be perpendicular to each other. Okay, so the slope of segment TA is going to be the negative reciprocal of the slope of segment ME. This negative reciprocal to the slope of segment ME. And the reverse is also the case. So the slope of segment ME is also the negative reciprocal of the slope of segment TA. It just depends on what you know and what you need, so you just figure it out accordingly. Alright, so now we have the slope of this line. I want to write down the equation of this line. So I need the slope of ME. So that's what I'm looking for. Alright, so I know that the slope of TA is given, right? The slope of TA is, I wonder what that is. We're going to use this equation, y equals mx plus b, the point slope form of the equation of a line. If we align it with the equation of the line containing segment TA, y equals negative x plus 3, what can you deduce from that? Well, there's an invisible one here. Let's put that in there. The coefficient of m is your slope. Okay? So based on the slope-intercept form of the equation of a line, we can clearly see this is line TA right here. Okay? We can clearly see that the slope of line TA is going to be negative 1. Okay? So the slope of line TA is negative 1. So it follows that the segment containing TA will also have a slope of negative 1, right? Perfect. Now that we have the slope of segment TA, we can use that to figure out the slope of segment ME. We just substitute it into this equation right here. So it's going to be the negative reciprocal of the slope of segment TA, which is negative 1. So if we simplify this, we have minus 1 over minus 1. What is minus over minus? Slash and dash, right? Positive, so it's going to be 1. So the slope of line ME is 1. Okay, now so if we want to write down the equation of that line, we can either use the point slope form or the slope intercept form. Okay, so a lot of students like the slope intercept form, so I'm going to use that. We already know that m is 1. We need to find b. Okay, b for the line containing segment ME. So we have y equals mx plus b, and we have the point that the line goes through is 2, 1. So this tells me that x is 2 and y is 1. So let's pull all that together. Pull all that together, we're going to have y is 1 equals m, which is 1, times x, which is 2 plus b. We're trying to find b here, okay? So 1 equals 2 plus b. If you subtract 2 from both sides, that gives us a b value of negative 1. Alright? So b is negative 1, m is 1. That's enough information for us to write down the equation of a line. We just plug it into the y equals mx plus b formula, and we're going to have y equals 1x minus 1 as the equation of the line containing segment EM. Okay, so our answer is option number 1. Alright, let's take a look at number 15. It says the coordinates of the vertices A and B of triangle ABC are 3, 4, and 3, 12. if the area of triangle ABC is 24 square units, what could be the coordinates of point C? Okay, so before we get started, let's talk a little bit about area of a triangle. What is the formula for the area of a triangle? I'd like you to recall that the area of a triangle is 1/2 multiplied by the base times the height. Okay, so if you have the area and one of these measures, you can simply find the other. So hopefully if we give ourselves a visual, we can determine what we have, either the base or the height, and then we can set up an algebraic equation and solve for the other missing piece, which could hopefully tell us what the coordinates of point C is. Alright, so we have to make sure that our sketch is 100% accurate here, because it's necessary to find the correct answer. So let's go ahead and sketch the triangle. Okay, so let's see. I'm going to draw my triangle right here. Okay, so first point, 3, 4. So let's graph that. 3, 4, 1, 2, 3, 1, 2, 3, 4. Okay, that is point A. The next one is 3, 12, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's point B. Okay, so this is 3, 12, and this one right here is 3, 4. Okay, we have a triangle. Where is point C? Where on earth is point C? That's what we're looking for. We don't know. Okay? But we know that the area is what? The area is 24. Okay? So this kind of sort of looks like the base of our triangle. So what's the length here? The length here is the base is simply going to be the change in the y's, because you notice the x is uniform. So the base is going to be 12 minus 4, which is 8. So if the base of a triangle is 8 units long and the area is 24 units, can you find the height? Absolutely. So we have a 1/2 b times h. So the height is unknown. So we're going to substitute into this equation here, because this is the equation, the formula that relates the three measures. So 24 equals 1/2 times the base times the height. Okay? Now let's solve this resulting algebraic equation for h. So we have 24. 1/2 of 8 is the same thing as 8 over 2 is 4. 4 times h is 4 times h is 24. So divide both sides by 4. And that gives you an h value of 6. Okay? So where is the height of 6 going to be? So h equals 6. If we want to create a triangle to find point C, any point that is 6 units from a line containing this segment, okay? If the distance from the point to a line containing this segment is 6 units, of course it shouldn't be collinear with these two, or else you'll have a triangle. Then you will have point C. So there are infinite number of points all over the place that can work. But let's look at the options. It's nice here because we have 4 options. Let's graph these points and see which one is 6 units from this line, perpendicular distance of 6 units, and then we can know for certainty that that will tell us the location of point C. Okay, so let's graph the first point, 3, 6. So let's see, 3, 6, 1. So this is 4, 5, 6. How is this point 6 units from? Is the perpendicular distance from this point to this line to this segment 6 units? The answer is no. The distance is just 0. So this doesn't work. How about 8, negative 3. So 8. So this is 3, 4, 5, 6, 7, 8. And then we're going to go down negative 3. Let me scroll down a little bit so you can see what's going on. Okay, so this is point 1. It was a fail. It's 3, 6. Now the next one is 8, negative 3. So we have 8, negative 3. So 3, 4, 5, 6, 7, 8. 1, 2, 3. Bam. Okay, so what's the alt? If this were point C, what would the height be? The height is going to be, we'll just extend this side, extrapolate this side right here. That will be the height. It will be 1, 2, 3, 4, 5. Oh, that was close, but that's not good enough. The height is going to be 5, but we need the height of 6. Okay, so this one is close, but it's not good enough. Now let's take a look at the next candidate, which is negative 3, 8. Let's see where that is. Negative 3, 8. Let me take this out the way so it doesn't confuse our understanding. All right, negative 3, 8. So 0, 1, 2, 3. That's negative 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. Bam. Okay? So remember, we're just looking for the distance from this point to the line containing this segment. So how long is this distance right here? 1, 2, 3, 4, 5, 6. Perfect. This is exactly what we want. This is point C. Why is this point C? Because if this is the third vertex of our triangle, it's going to create a scenario where the height is 6, and since the base is 8, the area is going to be 24, which is exactly what we're looking for. So the base is 8, and the height here is 6. Answer to question 15 is option number 3. Thank you so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments, just place it in the comment section below, and we'll be more than glad to respond. We update our YouTube page with videos on a consistent basis, so do subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on mathgotserved.com. Thanks again for watching, and have a wonderful day. Goodbye.